Hi friends, welcome to ASM Scientific. Dive into the wonders of the universe with our engaging space science videos, exploring galaxies, comets, and the mysteries of astronomy. We also delve into the fascinating world of psychology, bringing you insightful content that bridges the cosmos and the mind. Subscribe to ASM Scientific for a journey through the stars and beyond. In this video, I'm going to tell you these topics. So let's start the video. The Sun, which is essential for life on Earth, is a complex and ever-changing star with many intriguing behaviors. One of the most fascinating of these behaviors is the periodic reversal of its magnetic field, where the Sun's north and south magnetic poles switch places. This process happens approximately every 11 years and is a key part of the solar cycle. In 2024, scientists and those interested in space weather are paying close attention to the Sun to see if this magnetic field flip will occur this year, as it is a significant event that affects solar activity and can have various impacts on Earth. The Sun goes through an 11-year cycle called the solar cycle, during which its activity levels change. This includes variations in the number of sunspots, dark spots on the Sun's surface, solar flares, sudden eruptions of energy, and coronal mass ejections, large expulsions of plasma and magnetic field from the Sun. These changes significantly affect space weather, which in turn influences the Earth's magnetic field and upper atmosphere. Central to the solar cycle is the Sun's magnetic field, which completely reverses every 11 years, with the north and south magnetic poles swapping places. This magnetic field reversal is a crucial element of the solar cycle and is key to driving the Sun's activity. The Sun's magnetic field is generated through a complex process involving the movement of electrically charged particles within its interior. This process is known as the solar dynamo. Inside the Sun, the hot plasma composed of charged particles is in constant motion due to convection currents and the Sun's rotation. As these charged particles move, they generate magnetic fields. One of the key factors contributing to the complexity of the Sun's magnetic field is its differential rotation. And like a solid body, the Sun does not rotate uniformly. The equator of the Sun rotates faster than its poles. This difference in rotation speeds causes the magnetic field lines to twist and stretch over time. Imagine rubber bands being twisted and tangled, gradually becoming more complex and intertwined. As the solar cycle progresses, the twisting and tangling of the magnetic field lines become more pronounced. The differential rotation continues to distort the magnetic field until it becomes highly stressed and unstable. At a certain point, the magnetic field lines can no longer maintain their tangled state. They begin to break and reconnect in a different configuration. This reconnection process is what causes the magnetic field to flip. During a magnetic field flip, the north and south magnetic poles switch places. This is a significant event in the solar cycle, as it marks the transition from one cycle to the next. The flip is not an instantaneous process. It takes several months to a few years to complete as the Sun's magnetic field gradually reorganizes itself. The flipping of the Sun's magnetic field is crucial because it plays a major role in driving solar activity. During periods of high solar activity, such as solar maximum, the magnetic field is highly dynamic, leading to an increased number of sunspots, solar flares, and coronal mass ejections. These solar events can have significant impacts on space weather, affecting satellite operations, communication systems, and even power grids on Earth. Understanding the solar dynamo and the process of magnetic field flipping is essential for scientists studying the Sun and space weather. By observing the behavior of the Sun's magnetic field, scientists can better predict solar activity and its potential impacts on Earth. The study of the solar dynamo also provides valuable insights into the fundamental processes that govern the behavior of stars and other celestial bodies with magnetic fields. In summary, the Sun's magnetic field is generated by the movement of electrically charged particles within its interior through the solar dynamo process. The differential rotation of the Sun causes the magnetic field lines to twist and tangle, eventually leading to a magnetic field flip where the north and south poles switch places. This process is a key component of the solar cycle and plays a crucial role in driving solar activity and influencing space weather. scientists employ a variety of indicators to predict when the sun's magnetic field might reverse. One crucial metric they observe is the number and polarity of sunspots. Sunspots are temporary, dark areas on the sun's surface created by intense magnetic fields. These regions appear darker because they are cooler than the surrounding areas. As the solar cycle advances, the number of sunspots gradually increases, reaching a peak during the solar maximum, before declining as the cycle progresses. The solar maximum is a phase of heightened solar activity, characterized by an increased frequency and intensity of solar flares and coronal mass ejections. Solar flares are sudden eruptions of energy and light, while coronal mass ejections involve large amounts of solar plasma and magnetic fields being hurled into space. This period of maximum solar activity is also when the sun's magnetic field is most likely to undergo reversal. During this time, the sun's magnetic field becomes highly dynamic and unstable, setting the stage for a potential flip. One of the key signs that scientists monitor to predict a magnetic field flip is the change in the polarity of sunspots. Sunspots exhibit magnetic polarities, either north or south, depending on the orientation of their magnetic fields. As the solar cycle nears its peak, the polarity of new sunspots begins to show a pattern indicating the upcoming reversal. By closely observing these changes, scientists can anticipate when the magnetic field is preparing to flip. The careful monitoring of sunspot numbers and their polarities provides valuable insights into the complex dynamics of the solar cycle and helps in predicting significant solar events. This knowledge is crucial for understanding the behavior of the sun and its impacts on space weather, which can affect satellite operations, communication systems, and power grids on Earth. As of mid-2024, we are nearing the peak of solar cycle 25, which commenced in December 2019. During this period, there has been a consistent rise in solar activity, marked by an increasing number of sunspots and various solar events. Data from solar observatories and space weather monitoring agencies indicate that the sun is currently experiencing its solar maximum. This heightened activity phase strongly suggests that a magnetic field flip could occur this year or in the near future. Solar physicists are diligently monitoring the sun's magnetic field and sunspot behavior to make precise predictions. They use advanced instruments, such as the Solar Dynamics Observatory (SDO) and the Solar and Heliospheric Observatory (SOHO), to capture detailed observations of the sun's magnetic field and its fluctuations. These tools allow scientists to closely track changes and gain deeper insights into the processes leading up to a potential magnetic field reversal. While a magnetic field flip is a natural and regular part of the solar cycle, it carries significant implications for both space weather and Earth. One of the most immediate consequences of a magnetic field reversal is an increase in space weather events. As solar activity intensifies, we see more frequent and powerful solar flares and coronal mass ejections (CMEs). Solar flares are sudden eruptions of electromagnetic radiation, while CMEs are massive bursts of solar wind and magnetic fields expelled into space. These heightened solar activities can have a range of disruptive effects. For satellites orbiting Earth, increased radiation from solar flares and the physical impact of CMEs can lead to malfunctions or even complete failures. Communication systems, which rely heavily on satellites, can experience interruptions or degraded performance. Navigation systems, such as GPS, can also be affected, leading to inaccuracies and potential safety concerns for aviation and maritime operations. Additionally, astronauts in space are at greater risk from increased radiation exposure, necessitating better shielding and planning for space missions during periods of high solar activity. On Earth, geomagnetic storms triggered by enhanced solar activity can have profound impacts. These storms occur when CMEs interact with Earth's magnetic field, causing fluctuations that can disrupt power grids. Such disruptions can lead to widespread blackouts, damage to transformers, and other critical infrastructure failures. The financial and logistical challenges of these impacts necessitate robust preparation and mitigation strategies. Moreover, geomagnetic storms can also produce spectacular auroras, commonly known as the northern and southern lights. During periods of intense solar activity, these auroras can be visible at much lower latitudes than usual. providing stunning natural light displays in regions unaccustomed to such sights. To manage these potential impacts, scientists and engineers are working diligently to improve space weather forecasting. By enhancing our ability to predict solar flares, CMEs, and geomagnetic storms, we can better prepare for their effects. This involves developing advanced technologies and strategies to protect satellites, maintain communication and navigation systems, and safeguard power grids. Effective forecasting and mitigation efforts are crucial for minimizing the risks and ensuring the resilience of our technological infrastructure in the face of increased solar activity associated with a magnetic field flip. The potential flipping of the Sun's magnetic field in 2024 is a pivotal event in the ongoing solar cycle 25. This magnetic field reversal, which happens approximately every 11 years, is a natural and essential part of the solar cycle. As we approach this critical juncture, scientists are closely observing the Sun's behavior and refining their predictive models to better understand this complex and dynamic process. Monitoring the Sun's magnetic field and solar activity involves using sophisticated instruments and satellite-based observatories, such as the Solar Dynamics Observatory (SDO) and the Solar and Heliospheric Observatory (SOHO). These tools allow scientists to gather detailed data on sunspots, solar flares, and coronal mass ejections (CMEs), all of which are influenced by the Sun's magnetic field. By analyzing this data, researchers gain valuable insights into the mechanisms driving the solar cycle and the timing of magnetic field reversals. Understanding the Sun's magnetic behavior is not just an academic pursuit. It has practical implications for life on Earth. The Sun's magnetic field and the associated solar activity can significantly impact space weather, which affects satellite operations, communication systems, navigation technologies, and even power grids. By improving our knowledge of the Sun's magnetic field dynamics, we can better anticipate and mitigate the effects of space weather on these critical infrastructures. As scientists refine their models, they are developing more accurate forecasts of solar activity and potential magnetic field flips. These improved predictions help space agencies and other stakeholders prepare for periods of increased solar activity. For instance, better forecasts can inform satellite operators when to take protective measures to safeguard their equipment from solar flares and CMEs. Similarly, power grid operators can use this information to reinforce infrastructure and prevent disruptions caused by geomagnetic storms. Even if the magnetic field flip does not occur exactly in 2024 but slightly later, the ongoing research and monitoring efforts remain crucial. They highlight the intricate and ever-changing nature of the Sun, a star that continues to surprise and challenge our understanding. Each solar cycle and magnetic field reversal adds to our growing body of knowledge, helping us to unravel the mysteries of our nearest star. In summary, the anticipated flipping of the Sun's magnetic field in 2024 is a significant event within solar cycle 25. Scientists' efforts to monitor and understand this process provide valuable insights into the Sun's magnetic behavior, enhancing our ability to predict and prepare for the challenges posed by space weather. Whether the flip happens this year or shortly thereafter, it underscores the dynamic and evolving nature of the Sun and its profound influence on our technological world. If you like space exploration, galaxies, comets, astronomy, astrophysics, psychology, black holes, mystery, and many more science-related videos, then like this video and subscribe my channel. Thanks for watching. See you in the next video.